Start the next little video. So now let's go back to the problem. So we've got a 10 microfarad parallel plate capacitor connected to a 16-volt battery. After it's fully charged, the battery is disconnected without loss of any charge. Voltmeters connected across the two plates without discharging them. What does it read? That seems completely silly. Seems like it should just read 16 volts.
I know what I would think.
I'm going to put it and see if that's right. Yeah, because I mean, basically you're using the battery to charge up the capacitor. So now, I mean, we could compute the charge on each one just using the, well, I didn't actually write it down, but the definition was F equals Q over V. So we know what F is, we know what V is. We could find Q if we wanted to. After you disconnect the battery, though, I mean, if you fully charge it up after you disconnect the battery, I mean, before it was the battery creating the potential difference. Afterwards, it'll be the charge on the plates creating it, but it's going to be the same thing as the battery was to begin with. So, okay. Now if we charge it up and we separate the plates, now it's going to change, right? Because the charge is the same. Let's go back to it. The charge is staying the same. But if I look at this over here, well, the area of the plates isn't changing. Epsilon's not changing. Oh, crap. Sorry. Somebody's sick at my church, apparently. The prayer chain called. Okay, so A is not changing. Epsilon's not changing. It's still got air in between them. But the distance between them is doubling. So if I double the bottom, what happens to the other side? Well, the capacitance, I mean, if I double the bottom, the other side is going to cut in half, right? So the capacitance is cutting in half. Okay. All right, so this thing is being cut in half because I doubled the bottom of the other side. But that's not what it's asking for. It doesn't say what happens to the capacitance. It says what happens to the potential difference, right? So if I cut the capacitance in half, leave the charge alone, what's happening to the potential difference? Now say what you just said a second ago, Cindy. Yeah, you're doubling it. So the volts is...
Doesn't it really double is what I was thinking.
Yeah. Sorry, I was taking one more step to get there. Yeah, if you double the distance, that means the capacitance cut in half, which does mean the potential is doubled. So you're right. I was just taking one more step to get there than y'all were. Okay, what would the voltmeter read if the radius of each plate was doubled, but the separation was left unchanged? Okay, so going back again. So now it's saying the radius of each plate is doubled. We don't have radius in here, but we have something that depends on radius. What do we? Yeah, the area, right? If I double the radius of the circle, what happens to the area? Okay, area of a circle is pi r squared, right?
Yeah.
So if I double r, what happens to r squared?
It double. Well, it does more than double.
Yeah, it does more than double, right?
True.
Yeah, it multiplies by 4, right? Because it's like if you get twice as big both directions, I mean, that's 2 times 2, you got 4, right? So if I double the radius, the area multiplies by 4. So the capacitance is multiplying by 4, right?
From the original.
Yeah, compared to the original, this F is now 4 times bigger than it was. Yeah, from the 16. So we're not separating it now. So the F is now 4 times bigger than it was. If F is 4 times bigger and Q is the same, what's happening to V? So for part C, F is being times 4. Q is the same. So V has to be doing what? Yeah, that's going to be times a fourth. Right? So if the original guy was 16, now a fourth of that is going to be 4. So this kind of helps us get some intuition for what this is, because again, this potential difference is like potential energy per unit of charge, right? So it's kind of like energy, even though it's, I mean, you think about it like energy, even though there's really a per unit of charge in there. So you think about, okay, if we scoot the plates further apart, it takes more energy to kind of hold everything there. On the other hand, if we make the plates bigger, it takes less energy. So you get more energy if you scoot them apart or if you make the plates smaller. All right. Cool. Let's do one more kind of just in a row. Let's see what's next. There's probably another one about like that. Okay, so now we got a bunch of stuff connected in series and in parallel. So let's talk about that right quick, which again, you could just wait and skip to the end when I write down the answer, but I'm going to show you where the answers come from. So say we got 2 capacitors connected in series. Actually, let's do the parallel first. It's a little easier. Okay. So, by the way, this is called parallel. And this other one was called series. Just kind of a fact of life. If you're going around a circuit, we'll talk about circuits more. Well, we'll start talking about them in lab today. But we'll talk about them a whole lot more starting in homework 4. But when you go around a circuit, basically anywhere it branches like this, the potential difference from here to here, it has to be the same if you go that way or if you go that way. I mean, if it was greater one way than it was the other, I mean, the electrons would pick electrons like high potential, so they would pick whatever one's bigger. So if you're going to have like a steady stream or whatever, then it's got to be the same either way. So the potential difference is the same top or bottom. So let's say I put capacitance like F1 on one of them, and F2 for the other one. Well, the potential difference is the same either way, so let me just call it V. If I go back up here, F is Q over V. So if I want to find the charge on each one, Q would be V times F, right? So my charge on my top plate is F2V. The charge I'm going to build up on the bottom plate is F1V.
It should be the same.
If the capacitors are the same, they'll be the same.
Okay, that's what
But
you're saying.
again, what's the same is the potential difference either way.
I'm with you.
When we do the series one, the charges will be the same. But okay. So if I think about this as one huge capacitor, if I want to kind of replace this diagram with saying, okay, let's pretend like this entire box is just one big capacitor with capacitance F. Well, how much charge is it holding? It's holding Q1 plus Q2. So we'll call that Q. This is F2V plus F1V is Q. So if I think about this Q as being the capacitance of my big guy, the combined capacitance, times V, well, it's really simple. You just get F2 plus F1 is F. So this is for capacitors in parallel. So if you hook up capacitors together in parallel, their capacitances add together. And just so they'll be right together, let me go ahead and tell you the answer to the other one. If you add them in series, it turns out that their reciprocals add together. We'll show where this comes from right quick, but just so you know. So to get that, again, just draw the picture. Well, whatever Q I have here, I'll have minus Q there. If I think about this plate, well, if this plate had a different charge, then, I mean, I've got this wire connecting this plate to that plate. Like, the charges between them would want to travel along the wire and kind of even it out, right? So if I connect these up in series, I'm definitely going to have the same charge on the second set of plates that I had on the first set of plates, right? So if this plate has F1, this plate has F2, if I think about the potential difference from end to end, well, it's going to be whatever it is on the first one plus whatever it is on the second one. So here, my V is, well, go back to the formula. F is Q over V. So V would be Q over F. So my potential drop across the first one is Q over F1. My potential drop across the second one is Q over F2. So my potential drop across the whole thing is Q over F1 plus Q over F2. So again, if I want to pretend like, hey, let's pretend like this thing is one huge capacitor, what would be going on? Well, pretend like this V is just for one big guy. And my pen quit writing. I hate it when it does that. There we go. So this is Q over F. So I can cancel out all the Q's. You get 1 over F is 1 over F1 plus 1 over F2. Just like we prophesied a second ago. So basically, if you have them hooked up in parallel, the capacitance gets bigger. If you put them in series, the capacitance is actually smaller than either one of the two that you started with. So it's kind of, that's kind of weird.